So I'm going to be honest, I think this is going to suck. This is going to be one of the hardest things I've tried to do in a long time in programming. I'm not looking forward to this at all. But sometimes you just got to work your freaking ass off a little bit. So next I'm going to search online. This is the thing I'm looking for. And so in here is a you know what, let's start by going through some of these programs, what they do. So it loads the number 1 into the A register. This stores A to this memory location, which coincides with the pixels here. Then we're loading into the A register number 5, sending it to this memory location, then the number 8, sending it to this memory location. So it's going to be the first 3 pixels here. The numbers 1, 5, 8, if we look at the notes, 1 is white. So notice they don't use 0 because black you wouldn't be able to see the background. 5 is green. I know it's very small. Let's make this bigger, huh? Make it bigger! I think that's good. Yeah. It does that. There's a debugger. I haven't bothered with it. I guess it's just, it's not going to be hard. If I feel like I need a debugger at some point, I don't think it's going to be too hard to come back and figure that out. Registers. So we have an A, X, and Y registers. A is often called the accumulator. Each register holds a single byte. Yesterday I did work with a stack. We're going to see it later. There's a bunch of flags. We'll see it when we come to it. So let's see what's happening here. So we're loading this number. Now this is hexadecimal. So the letter A here, well, first off, if you had the letter A here, that would be the number 10. B is the number 11. F is the number 15. So if you have a 1 here, that's the number 16. So if you had, let's see, if you had an A here, that would be 160. And I believe this is the number 192, I believe. So we load that into the A register. That's what this command does. Now, TAX is going to transfer A to X. Whatever's in the A register gets transferred to the X register. Here we increment. I mean, it's got the things here, but we increment the X register. ADC, I guess this is adding. I believe this is add with carry. So yeah, it adds hex value to the A register. Okay, so I think it's just adding 2 numbers is what's going on here. 184 is 2. Oh, okay, so Adding these would give 184, but the processor gives the result 84. So there's a overflow. So if you're looking carefully enough, you'll notice that the carry flag was set to 1. So that's what the carry flag is about. It's supposed to show when there's overflow. I didn't know that. Bender in Futurama has a 6502 processor for a brain. Interesting. This is better below type this, don't paste, blah, blah, blah. So this is loading the whatever that number is in hex. Hexadecimal. This is not complicated stuff. Distinction between these two. So this is a memory address, whereas this is the number 1. Second is the value stored at memory allocation, memory location 1 to the A register. Okay, important distinction. Blah, blah, blah. I don't know. I don't really want to read everything here. But we've done some branching. We did it yesterday. Branch on not equal is very common. We studied this one. It loops through and decrements. I guess I'll just explain how this is working. So load X. I load into the X register the number 8. And so this is going to act like a loop. This is a label, and you can see this refers back to the label. Okay, so anyway, so we've loaded 8 into X, then we decrement X, so it should be 7. Now we're going to store X at this memory location. This memory location corresponds to the first pixel here. And now CPX is to compare X to the number 3. And so at first X is 7, so it compares it, and this sets a flag to 0 or 1, true or false, depending on the result of this compare. So since they're not equal, it sets the flag to 0. And I believe it's called the Z flag. I don't know why it's called that, but yeah. And so then on the next instruction, this is branch if not equal. So if this came out false, it will branch. So at first X is 7, so it does a compare, it comes out false. So this will branch at first. So it comes back up here, decrements again, so now X is 6, checks again, still not equal, and then it branches again. And so X keeps going down until it's 3. Then it will compare the values, it will get true, so the Z flag is set to 1. Goes to this, and it does not branch this time, so it skips that instruction. Now we have STX, so store X to this memory location, which is going to be the second pixel here, and then break. So since this was looping, I'm guessing the first pixel will be well, I think these pixels will be the same color. So let's check that. Yeah, they're the same color. So it kept changing the first pixel until it got to 3, and then it stores it also in the second pixel there. By the way, anybody can ask questions if you've got any questions. So this just explains what just happened. So it's nice because it's a little loop. The opposite of BNE is BEQ, so branch if equal. So then we have BCC, BCS, branch on carry clear, branch on carry set. So yeah, okay, that'll be interesting later, because remember carry was related to overflow with flags and stuff like that. So we could use that for branching. So there's a 16-bit address bus, so this is how much memory we have available to the processor. Bytes are represented by 2 hex characters, so it looks like this. So So I think 65, well, I think 65,535 is probably F in hexadecimal. There's one more byte because we count 0. Let's see here, because there is a memory monitor here with this software they have online here, which is nice. So we'll figure that out if we want to use it later. And there's a bunch of stuff about paging and stuff. I think this is mainly about making things faster, actually, which I'm not too concerned with right now. I haven't looked at this code. Let's see. I don't see the... Okay, not equals down here. Let's see what this does. So load into A, the A register, the number 1. Compare with the number 2, so it's going to be not equal. And so it should just branch, and then break. Okay, is that it? Oh, it's telling us to then look at the memory. Okay, I don't really care about that right now. Some instructions don't deal with memory locations, right? It's talking about a bunch of different addressing modes, which is a little... I don't quite need so much yet. There's a number of ways to sort of address or access memory. Now it talks about the stack. So I did this yesterday a bit, and that was nice. So, all right, what I'm gonna do is try to do the same thing I did yesterday without looking. So I'm just gonna grab, yeah, let's just get rid of this and use this here. So what I did yesterday, ultimately what I want to do is write a function where it receives some kind of input, like let's say it receives the number 4, and then it will output all the possible permutations of 4 elements. So for example, it will output 1, 2, 3, 4. It will output 1, 2, 4, 3, and so on. So if you want to think of it as like there's a first place, second place, third place, fourth place, and then like all the reorderings of that, if you will. So that's my sort of, yeah, my goal here. And I mean, I'm somewhat new to assembly. So yesterday, so let's start with input to the program. So LDX, I'm just going to say, is the number 4. Actually, we need a thing like that. So that's the number 4. And then, so I'm counting that as the input. So if I were to output 4, 3, 2, 1, it's kind of easy. I just make a loop that decrements. But what I did yesterday is I used the stack. I wanted to output 1, 2, 3, 4, the opposite order. And I used the stack to do that. I'm sure there's better ways. So I might figure out better ways at some point. But let's maybe try to do what I did yesterday. So I'm going to have some kind of loop 1, let's say. And what are we going to do? We're going to decrement x. And so that's dex. But first I want to, we're kind of printing, which all I know to do right now to get output to this is to print pixels onto the screen here. So my version of print is, I believe, we'll send whatever's an x to A. I think we can do that. Let me bring up a cheat sheet for 6502 here. Yeah, we had this one yesterday. Oh, I love how when I zoom it, like stops me from actually zooming in. Basically, this is great. Okay, anyway, we got it on the computer, and TXA should be a thing. Yeah, it's totally a thing. So these transfer commands just move data between registers. We have TAX, TAY, TXA, TYA. So these are not complicated instructions by any means. These three, LDA, LDX, LDY, they just put something in the register, so that's what I did here. That's very simple. So let's send that to the A register, and then we are going to, was it store? Yeah, store the A register at a memory location, which is going to be, this will be the first pixel. Now this is just going to loop forever, which I don't want. So I'm going to put a break. And let's see, yeah, this is corresponding to the number 4 in this little world. And so that's doing what it should. So now we want to loop through here, decrementing, basically counting down this number 4 as a next step here. So let's see. So after this, I'm going to decrement x. I think I also want a y value. Well, let's initialize a y value of 0, I guess. Okay. And let's decrement x and increment y. And so we can add an offset here. So we do that. Was it just like this? I think we just do this. And so this will have an offset. So as we increment y, it should increase. And then we want to add a compare so that, yeah, because loops need some kind of compare statement. So I believe we do, is there a CMX? I think. Let's see here. CPX, compare the X register. We're going to do CPX. And we're going to put a number here. So we want to compare with the number 0, and then branch if not equals, because we're decrementing X. So branch on not equals, and we'll branch to here. And now I don't need this break statement anymore. So hopefully this, let's see what happens here. Yeah, so we get, it's counting down 4, 3, 2, 1, based on the colors that we have set up. So what I actually wanted to do is to go 1, 2, 3, 4, not like this. So what I'm going to do is I'm going to use a stack. I'm going to, instead of printing them here, I'm going to put them on the stack. Okay, so instead of printing, we're going to, there's PLA is pull from the stack, and then there was what was it? Let's see if we can find it. Yeah, PHA is push. Oh, we can directly push X register or Y. Okay. So PH is for push, PL. We can PLA, PLX, PLY. Okay, good to know. So I want to, maybe I don't even need to put things in the A register at all. We'll just push the X register onto the stack. Okay, and we don't need to bother incrementing Y right now either. So this is, what I'm doing here is already simpler than what I was doing yesterday. So I think I'm upgrading to a little bit cleaner code here. I also think that putting this on the stack, having 2 different loops, which I'm about to do, putting it on the stack first and then having a second loop to print it out. There's probably better ways to do this also, but whatever. We'll figure things out. So we're pushing to the stack. And then we want another loop that is going to pull from the stack and print. Okay, so what I'm going to do is, let's just let's just PLA. So this is going to pull from the stack and put it in the A register. Then we can sort of print by taking what's in the A register, putting it at a memory location, which is going to be, yeah, just $, I think, with a Y offset. So I'm going to put the Y initialization right here at 0, 0. Let's increment Y. And is that gonna be good enough? It's gonna loop forever right here. So we need some kind of compare. And so let's, now I could sort of hard code like compare Y to the number 4, but that would be bad because the number 4 here is meant to be sort of the input of the program. We don't want to hard code that here. So instead, what I want to do, yeah, I remember this now. I'm gonna write this to memory, whatever is in the X register here. So can I just do STX? Yeah, I can do STX. And STX, we're going to put, let's just put it in memory location 1. We can do that, if I recall correctly. It should be a $. Okay. So, yeah, just let me scroll there. That was weird. So we're storing X, which is meant to be the input of the program, in this memory location. Now here with loop 2, we want to make use of that. So how do I take, oh, okay. So I think, okay, let's load into X. Whatever's at memory location 1. I think that's how that works. So now X, because in this loop, X was getting decremented. And so we lost the information of what X was originally. So now we're restoring that here. And now, let me think. So our loop, we want to be decrementing X. And we want to compare X with the number 0. Branch if not equal to loop back to the top of the loop. This might work. Let's see. Oh, syntax error line 4 for phx. Syntax error, huh? Oh, because I'm not... Why is that? I don't know, but maybe this software only... You can only push to the A register, maybe? Let me think. Wait, what are we doing here? Yeah, I want to take X and push it onto the stack. So anyway, so let's move X. So I'm going to transfer X to the A register, and then I'm going to push the A, whatever's in A, onto the stack. Okay. Yeah, maybe here I can only use PHA. I can't use PHX, PHY. So let's see here. So this corresponds to 1, 2, 3, 4. So this is working as intended. This is basically what I had yesterday. So this is a nice little one-up. And Now is the hard part. My goal is to make an algorithm that outputs all the permutations. So all of the reorderings of these 4 pixels will be sort of printed out. Yeah, it's going to be a little hard. It's going to be tough. So I might want a function that simply swaps 2 pixels. So I think, though, instead of putting things on the stack, I probably want to use putting things in memory rather than using the stack. I think the stack is a little faster. Has that little advantage. But so I'm going to redo this to not use the stack and just pop it onto memory in these memory locations. And so instead, let's use the stack for this initial value. So I'm going to get rid of loop 2 because we need to go back here a bit already. And so instead of stack, so we're going to use the stack for storing the initial value, and we're going to use memory for what I was previously using the stack for. All right, so actually, let's go all the way back to here. And forget about this for now. We can worry about that later. So whatever's in the X register, we want to... so I think I can do stx to a memory location, 0, 1. Should store X there. So I just want to make sure I don't get a syntax error. Yeah, no. Okay. Can we do with a Y offset as well? So let's load into the Y register the number 0 and see if we can do Y offset. No syntax error. Yep, seems to be fine. No syntax error. Okay, so that's good. So now we want to loop through. Let's just loop through naively 4, 3, 2, 1 rather than 1, 2, 3, 4. So, but we are going to have a decrement of X at some point. Before we decrement, we want to be making use of the value. And then we're going to want to compare X to the value 0. Hold on, the number 0. Then branch if not equals loop 1. Is going to work here. Already syntax error, CMX. CMX. Did I spell it wrong or something? I think it's CPX, yeah, okay. CPX. Okay. Now there's no output yet. Now we're not incrementing Y also. We need to increment Y. So hopefully in memory we have sort of 4, 3, 2, 1, like that in memory, hopefully. Now I want to make a second loop that is going to output this memory. So, loop 2. Let's see here with loop 2. Oh god. This is kind of new for me. So, I've studied assembly before, but I studied it a few different times out of interest, but I have never started really writing programs with it until yesterday. So, but it feels cool. It feels cool, but it's a little, because it's new, it's a doozy. But it's good. It's good. All right, so loop 2, we're going to output stuff here. So let's see here. We want to get it from these memory locations to... Let's start by sort of initializing Y as the number 0. Okay, so Y is back to 0. And then we want to get from these. Oh, so I guess to get the memory location data, we just do probably load. We can do like load A. And I'm just looking at the cheat sheet. I don't have this stuff written out or anything. But so I think we can do load A and then the memory location with the Y offset. And then let's send A to this other memory location. Again with the Y offset. Yeah, let's do it again with the Y offset. And this memory location prints onto the output there. Okay, so we need to be incrementing Y, and we're not even using X, are we? But we need to be using X because we don't have any way for this loop to stop yet. So again, I want to load into X whatever the initial value was, and that's where I was going to use the stack for that. Okay. So the stack, I want to transfer X to A, and then push A onto the stack. And then here I'm going to pull A, or I'm going to pull from the stack that goes into the A register. Then I'm going to transfer from the A register to the X register. So now in X we have our initial value of 4. And then, so we've incremented Y, and then I just want to decrement X like that, and then we're going to have a compare X with the number 0. That's the wrong thing. The number 0. Branch of not equals to loop 2, so it loops, and I think that might be it. We'll see. I don't know if this is going to have mistakes. It didn't assemble, I don't think. Syntax error, line 15. Line 15. I wish I had lines on the side here, but it says this. Does it not like having the offset here? I suppose with no offset. So this maybe it cannot have the offset. Huh. That can't have the offset, huh? Alright, well, I gotta figure out how to do the same thing but differently. Some kind of workaround. So I want a location in memory with an offset. Now we saw a lot of stuff they were talking about before with paging and addressing. Probably I can make use of that. So let's see, where's all that stuff for branching? Addressing modes. So we'll start reading through this and see if we can find the answer to the problem. Let's see here. With all these examples, you might find it helpful to use the memory monitor. Yes, absolute. Absolute addressing, which is probably straightforward. 0 page. All instructions that support absolute addressing, with the exception of the jump instructions, also have the option to take a single byte address. This type of addressing is called 0 page. Only the first page, the first 256 bytes of memory, are accessible. This is faster, as only 1 byte needs to be looked up. Okay. So but that's still absolute. We don't have any offsets. If the result of addition is larger than a single byte, the address wraps around. That makes sense. 0 page. Okay, so here, yeah, it has an offset. Can only be used with LDX and STX. This is the equivalent of 0 page X, but can only be used LDX. So was I trying to do LDA? I was trying to do LDA. I was doing LDA. So we can do LDX with the offset, but not LDA. Interesting. All right. So instead of... Okay, so I'm going to leave this data in the A register. And... So we just need to swap what we're doing with the A and the X registers here. So we pull onto... So the A register here is going to have the initial data, the input of the program. Okay. And so we want to load to X this thing. And can we decrement A then? The DEA? The Drug Enforcement Agency of decrements? Let's see. Can we do that? DEA. Decrement the accumulator. Nice. And we can increment as well. Okay. And INC and DEC, increment and decrement memory. I'm not sure what that does. Hopefully we'll learn at some point. Okay, so we can DEA instead. So we're loading into the X register the data that we want. Okay. Now instead of storing A, we want to store X here. We're incrementing Y because that's our offset. Decrementing A because that's going to be used for our compare. So can we compare A? Yeah, CMP will compare the accumulator, the A register. And so maybe this will work now. If this thing doesn't happen, we branch if not equal here. Let's see what happens. No, we have a syntax error. STX. Wait a second. Now you can't do this with, you can't do the offset with X? Is that how that's gonna work? Oh god, that's gonna be annoying. So 0, we just saw this. Then absolute Y can't be used with STX, but can be used. Wait, hold on. So absolute X and absolute Y. Here's an offset, 6502. Yeah, so it could be, hello Sido, welcome. It could be, yeah, Nintendo Entertainment System, the original. It could also be Apple II, Commodore 64. There was I think an Atari system or Amiga, I forget. The BBC Micro is a whole lot of stuff, yeah. Welcome, by the way. How are you doing? I'm somewhat new to it. I'm in the process of learning. So, okay, so we've got these absolute addressing methods with LDX and STX. Absolute can't be used with STX, but can be used with STA. I don't know why it says can be used with LDA, because I think we tried that before and it didn't work. So, okay, so this is going to make things a little... This is a bit of a obstacle or a monkey wrench in the business here. So this is what I'm writing here. Yeah, I'm good. I'm good. Thank you. Where are you from? Are you a programmer? Okay, so we can't do STX. All right, so let's start over with loop 2. So what we have, and I think PLA, I think we want that. So what we have is memory is getting written into these 4 bytes in memory. Loop 1 is doing that. And we have this X value. This is, I'm kind of treating this like the input to the program. So our input is the number 4. And, but I push that onto the stack, and here I pull it off the stack. So it's in this register A. And yeah, so we can reuse it here for our next loop. So loop 2. So what we want to do is we want to get the information off of out of memory. So STX is okay. Wait. Okay, STX is okay. STA is okay. Can use this as well. But LDA, I'm getting confused. Yes, it's been a while since I've written anything in assembly, though. Nice. What kind of stuff do you usually, what languages do you usually write in? Or what kind of platforms or whatever? So I'm going to want some kind of LD something. We want to load information. And I think we want... Was it LDX that we want? Or LDA? Getting confused. What was I doing before? LDX. Okay. LDX. And then we have memory location with a Y offset. So we've initialized Y at, or reinitialized it really, at the number 0 here. The number 0 there. Okay, cool. So we're doing that. We want to increment Y. And I want to output information. We do that with a ST. And this is where I ran into trouble, because I did STX. And you can't do the offset. What are we going to do here? I don't know what to do here. I don't have enough registers. We only have 3 registers, and I'm out. I guess I need to use memory or the stack. Past few years has been mostly higher level languages: C++, C#, Objective-C. Oh, you write Objective-C. I wrote that like 8 years ago. Some Objective-C. Java. My employer at the time was pressuring me to use Swift instead. Yeah, it's a long story. So, what are we gonna do? I'm a little stumped. A little bit stumped, actually. With this information, maybe I can put this information somewhere else. But can I just put it somewhere in memory? Somewhere in memory. Okay, I have an idea. We're going to, instead of the memory location starting at 1, we're going to start at 2. We're going to start at 2, and the memory location 1 will be used for... We're not going to use a stack for this. We're going to... Let's see, store... I should be able to store X at memory location 1. So the memory location 1 is where we're storing the initial value of the program. I hated Swift. It took forever to compile. Oh, yeah? Objective-C is extremely verbose, right? But you have the auto completion, so I kind of enjoyed it. I kind of liked that it was very verbose, because you could just kind of read. I feel like it made it easier to read things and see what things are doing. But yeah, I mean, my employer wanted me to use Swift, but Swift at the time was fairly new, and so Apple, their example code that they had way more stuff in Objective-C. So like, I got started working on the app with like 1,000 lines of code from Objective-C from Apple's example code, and if I were gonna do that in Swift, I'd have to write it all in Scratch or from scratch. They didn't have the example code in Swift, so I didn't last very long at that job. We had a number of that boss was kind of an idiot. It was kind of funny, but it was fun. But yeah, I didn't last too long there. Anyway, that boss, I would have to. He'd come up with all these crazy ideas that were bad, and you could never like change his mind on anything that day. But I would always explain something to him, like I would like to change his mind on something, but I'd explain something to him, and then like he would change his mind, but he needed a day. Like he would sleep on it, and then his mind would just be changed. So that's better than never changing your mind, admittedly. But when you would actually talk to him, he'd be super stubborn and never give way. But then the next day, his mind would be changed, and he'd act like it was his idea. I don't know. Maybe that was just his. He thought that as a leader, he could never show any weakness and never look like he was changing his mind. I have no idea. It was weird. I kind of, yeah. All right. So let's see here. LDY 00. Cool. So now we are loading from this new memory position. We're incrementing Y. And now what I want to do is I want to get the initial input to the program again, which is stored at this memory location. So I guess I will... Maybe we load... I still have the same problem. We only have 3 registers. Oh wait, could I do something on the stack? There's one thing, there's increment memory and decrement memory. I don't know. So they're using that here. Oh wait, so this is this working like a pointer? Because they're supposed to increment memory. So what is snakehead L and that kind of stuff? I don't know what happened to this. Everything's underlined. It's very annoying to look at, actually. Snakehead L. They have these defines. Nice talking. I gotta get back to work now. Oh, thank you. Have a good one. Thanks. Okay, let's look through this code a bit and learn some stuff here. Even though these underlines are pretty annoying. So we have some macros that just define things as certain locations in memory. Okay, you got a bunch of those. So we can make use of that. Directions. Okay, this is working like enums, basically. Interesting. But there are more macros. ASCII values of keys controlling the snake. Okay, so we're gonna get input from the user. So this probably corresponds to arrow keys. Oh no, okay, obviously it's WASD. Okay. Hello. Saying hi? Nice. How you doing? Mr. Beast loving anarchist, how are you doing? System variables. Okay. I believe there's a random number generator they give you access to, so that's probably that. We have okay, so this is the program's starting. It's saying jump to the init, do init, then go to the loop. So we have an init snake function, we have a generate apple position function. So init snake does all this stuff, generate apple position does all that stuff. I hate that this is underlined. Why is it underlined? Whatever. So this is loading into the A register, moving right. Okay, so it starts moving right, then puts us in some snake direction variable. Number 4. So that's actually not a number. What is this? Or it's not hexadecimal. I see. So it's just a decimal number, huh? Right. We can just use decimal numbers. I forgot about that. I think we can do that. So start length is 2 segments. Okay, whatever. Loading into the A register. The hexadecimal number 11, which is the number 17. I don't know why it's doing that, because it's not commented. Store is to snakehead L. Snakehead L is meant to be the left. It says screen location of snakehead. Okay, so it's just choosing a place for where you start, basically. Okay. Then we're loading in the number 15. And this is something body segment 1. I don't know. This is a little complicated. I'm not understanding everything. Generate apple position. So it gets a random number, pops it into the apple location variable. Load a new random number from 2 to 5. So it does more random numbers. This is clear carry. Add with carry number 2. Add with carry number 2. No idea what's going on here, to be honest with you. Okay, we've got a loop. And so it has a bunch of functions, and this is the whole game loop. After that, it just goes back around, so it loops forever. Jump to loop. Okay. So it reads the keys, checks collisions, update snake, draw apple, draw snake, spin wheels. I'm guessing that's just doing everything else that you need to do. Read keys, just checking for a bunch of keys. Okay. I don't know if I want to look. But okay, so these snake lengths are memory allocations, and it's incrementing. It's incrementing it like it's a pointer. So this might be the information that I needed to fix my problem. I'm just sort of scrolling to see if there's anything else that's interesting. I think this is just return RTS. Where's RTS on here? Return from subroutine. Okay, yeah. Just return. So how's that different from break though? Break is break. I don't know. What exactly is going to be different with that? I'm not sure. LSR and BCS. What are those? LSR and BCS. LSR. LSR. It's here. Logical shift right. Okay, these are bit shift operations. LSR and BCS. 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 Branch on carry set. Ugh. So does the... I'm guessing that these... Says this is logical shift right, basically like a bit shift. Do those have... Do those affect the carry flag? I don't know. Right now I don't really care too much about doing bit shifting and all that kind of stuff. But okay, they explain everything in more detail here, so that's nice. But anyway, I think I have the information I need. This is the stuff I was working on. So it sounds like we can define. Okay, defines are going to help a lot as well. So, but I just want to check this syntax. We just write define. We don't need a hashtag or pound or whatever the frick. It just works like that. Okay. So where was I? Here. Wait, is this mine? No, this is not mine. This is mine. So we just do define something as something. Can I just define mem? Initial, so let's call it input as a 1. Okay, so what I'm doing is, instead of using the stack, I believe we can just stx. Well, you know what this might do? Never mind. stx to input. Okay. And so we're initializing. Well, it's not initializing because we're reusing the variable, but we're starting with, again, with y at 0. And now, instead of using y to increment, let's say memory, LDX memory. So we're loading memory into LDX. Okay. Then what I'm going to do, I'm going to increment memory. So now it's pointing 1 forward. And now I'm going to transfer X to a register. Then we're going to store A in this location. And we are going to need maybe Y as an offset. So we'll do that, and then I'll increment Y after that. Oh, baby, this is good. This is good stuff. I'm learning. One second, I'm grabbing more coffee. So it's cool. Like, we can basically, I figured out how to use pointers essentially. Very cool. All right. STA y increment y, and so we need some way for this loop to end. How is the loop going to end? The only way I know how to make loops end right now is through decrementing stuff. Are there other compares that we can do? Let's see here. CMP is compare accumulator, CPX, CPY. That's it. What are all these crazy symbols? Let's try to understand this a little better. So, for example, you have well, for example, a lot of these just have like IP2. Let's see. CMP has a lot of crazy stuff. CPX, IM2, Z3, AB4. Does Z3 mean you have all of these options? So AC is accumulator, so that's what this stuff is. IP I don't understand IP too much. IND, is it indirect? I think, but there's a Z flag. I don't know if that ZP is the Z flag. I have no idea. I'm trying to understand this. I mean, look for and. How much shenanigans is there? AB is absolute. So we have AX, AY. Okay, so it has these 3 different addressing modes for and. A lot of stuff I don't understand there. But it seems like all I can do with compare... Wait a second. Can we compare? I think we can compare, because there's an addressing thing here. We can probably compare to a value stored in memory. So, yeah, that would be nice. That'd be really nice if we could do that. So let's, okay. So as we increment y, it started at 0. Let's see if we can compare y with a value in memory, which is input. So input started at 4. Now, problem is 0, 1, 2, 3, 4 is 5 values. Okay, let's do something slightly stupid and store load into A input. How do I just subtract the number 1 from something? I don't know how to subtract to just do -1. I don't know how to subtract numbers for one thing. Subtract. SBC, subtract with carry. It's the only time they talk about subtraction here. All right. Let's write a simpler program. Let's just see if we can subtract a bit here. So SBC, they said. Where's that on here? SBC. Right here, subtract with carry. So we've got add with carry, subtract with carry, decrement memory, increment memory, all of these. So I understand all of this below calculate, although I don't understand the difference between break and return, but okay. No operation does nothing. I also understand all of these transfer commands. Transfer X to stack, transfer stack to X. Okay. So I imagine that would be like popping whatever's on the stack and then pushing X. Or, okay, so transfer stack to X probably, instead of popping, just copies the value. Would be my guess. We have pull Y, pull X, and push X, push Y. That stuff was not working in. Possibly it's not something you can use here. I think we could only do it with the A register. Then we've got PLP, processor status. I haven't really learned about the processor status here. So, but so far working backwards here, I think I understand everything except the processor status stuff. Now, branch on bit set, I have no idea what this stuff is. Hello, Zanny. How's it going? We're writing assembly. Do you know any programming? So SBC is subtract with carry. So let's write a little program. So load X, load into X the number 1. Let's say. Is it the other way? Yeah, it's the other way. So we're writing assembly. So this is 6502 assembly. It is the language that was used for the original Nintendo entertainment system. Okay, so what this does is it takes the number 1, puts it in the X register. The processor has 3 they're called registers. Basically, when it wants to compute something, that's what it has to work with. It can use these registers. For example, to add numbers, you first have to put the numbers in these registers. So that's what we're doing, putting the number 1 into the X register. Now we can sort of print that. We can stx will store X in a memory location. So we choose a memory location, and we're going to choose 200, which corresponds to the first pixel here. So if I run that, we have set this to white. The number 1 corresponds to the number white. So we have in the notes here, there's a bunch of zeros black and a bunch of colors. We have 16 different colors, including white and black here. So that's all we're doing. We're taking the number 1, putting it in the X register. Then we are storing whatever's in the X register at this memory location, which corresponds to the first pixel. Yeah. Do you have any programming experience, Zani? Welcome, by the way. Now what I want to do is I want to see if I can subtract 2 numbers. So the number 4 is purple. The number 3 is cyan. Number 2, I think, is red. So let's, yeah, okay, so start with purple. How do I subtract? So let's load into Y. We'll do this later. I want to see if it handles white space, all this space. Yeah, no problem with the space. So let's load into Y the number 1, and so can I figure out how to subtract it? So or let's do addition first, because I haven't done that. So addition was ADC, I think. Let's see, ADC. Where is, so I just want to go to the beginning of where they talk about it. I don't LOL. I ended up on the wrong side of YouTube. Cool, thanks for hanging out though. And alright, so instructions in assembly are like a small set of predefined functions. All instructions take 0 or 1 arguments. Okay, that's good to know. We don't have anything that takes 2 arguments. Here's some annotated source code to introduce a few different instructions. So this we've seen: load this value into the A register, transfer it from A to X, increment X. So ADC, this is adding. Add this value to the A register. I see. So I think we can only add or subtract with the A register, I'm guessing. So ADC. So ADC, let's see here. So we actually want to transfer X to A. Transfer X to A, okay. And then let's do ADC, the number 1. And then let's store A at the memory location. So that made it green. And the number green corresponds with 5, which is 1 more than purple. So it's adding the number here. We'll add the number 2 instead. We get blue. And check the notes. Blue is number 6. That's working as we would imagine. So what if we subtract instead? SBC. Then we started with purple, and I think we'll get red. White. Minus 2, so it should be the number 2. What's wrong here? 4 minus 2 is 2, and 2 would be not white, it would be red. What's going on here? Why is... I've done a little... Oh, hello, Luke Westfall. Welcome. I've done a little bit of assembly, including a tiny bit of 6502 for the Commodore 64. It's challenging, but a lot of fun. Yeah, I totally agree. This is day 2. Well, I've studied assembly several times before, and I've studied... I studied 6502 over the course of a few weeks, like maybe 6 months ago or something. But starting yesterday is the first time I've actually really been writing assembly. So my goal, which is going to take probably multiple days, but the goal is to write a program that will... so for example, if it takes the number 4 as input, it will then output all the possible permutations of 4 elements. So for example, I'll just explain that simply in case some people don't understand what that means. So for example, if it got the number 4, it would be like if you had first place, second place, third place, fourth place, and then it outputted all the possible reorderings. So it outputs 1, 2, 3, 4, 1, 2, 4, 3, 1, 4, 3, 2, 1, 3, 4, 2, like all these possible reorderings. That's my sort of medium-term goal here. Just a program that outputs permutations, all the possible permutations. So I think that's a nice, it's kind of hard, but it's a good little medium-term goal. So we're working up to it, because I'm just learning how to subtract numbers as well here. So yeah, where were we here? So well, ADC. Just a little confused because this is subtract. Okay, let's subtract by 1 first. It gets red. What about subtracting by 0? Shouldn't change anything. And if I get rid of this, why is subtracting by 0 changing something? Is that a bug? This is 0. Why would subtracting by 0 change anything? The heck? That's very strange to me. An important thing to note here is the distinction between ADC1 and ADC... Wait. No, yeah, I'm using this as numbers. I'm not using the memory location. ADC1 adds the stored value at memory location. The opposite of ADC is SBC. Subtract. Wait a second. Subtract with carry. Yeah. Honestly, don't know why. I feel like it should be subtracting 0, but let's see. 6502 SBC. Maybe there's something basic that I'm missing here. Subtracts the accumulator with a memory location or immediate data, but also subtracts the complement of the carry flag. Okay. Also subtracts the complement of the carry flag. Oh dear. So the complement of the carry flag. So I guess the carry flag is 0, so it's also subtracting 1. That is so freaking confusing to me. So do I just... Can I set the carry? Hold on. Set carry is SEC. So set carry... can I just do this? Set... I don't know if this is going to work correctly. No, it doesn't like that. Syntax error. If I don't have this... Okay. So now it's working the way I would expect. I guess I have to set carry first? I don't know. Let's look on here for what's going on with carry. Okay. Huh. It doesn't really explain about it. But, yeah. Okay. Where was I? I was here. And Okay, I kind of get it. I'm gonna use the restroom. I'll be back in a minute. So when you did Commodore 64 stuff, was that back in the day, back in the 80s, or was that more recent? So I'm honestly pretty surprised that I need to set the carry before doing any subtraction, but okay. Let's just verify again. So this corresponds to the color white, and I'm subtracting 0. So yeah, we are getting this. If so, the least significant bit there is the carry flag. If 1, then the carry is 1. Yeah, so I think setting the carry sets it to 1, and then this subtracts the complement. So the complement of 1 should be 0, right? It's either 1 or 0, right? And oh, but there's also clear carry. Yeah, so I get it. So set carry sets it to 1. Clear carry sets it to 0. It's interesting. So subtraction subtracts the number and it subtracts the value of the carry. I'm surprised. But I'm sure there's a reason for that. Probably find out at some point. So we're subtracting, hopefully correctly here. Yeah, so, okay, cool. So let's go back to the program I was trying to write, which is somewhere up here. Not that. Wait, where is it? Program I was writing is somewhere in here, hopefully. I think it's this one. This looks like my writing. Oh, not long, a few months ago I did a talk on 6502 assembly for a local tech group. I was born in 1990. Oh, okay. I was born in 87. Yeah, so similar age. That's cool. So far I'm really enjoying it. The reason I started studying it is I feel like I need medicine from all the tech is kind of a mess to me. Like any high level programming is kind of a mess. I mean, I guess probably C is my favorite programming. I like low level stuff. I like to really have control of what's going on. But actually, operating systems kind of bother me, like Windows, Mac. I prefer Linux, although I'm on Windows here. And I'd love to program on a device like the 6502 processor, where I'd like to be able to fully understand everything that's going on, right? Like we can, you can look at the 6502 architecture. I think they have images. There's some famous image, like they really mapped out everything, or I don't know if it's a reverse engineering job or what exactly, but yeah, somebody cut into it and photographed it, and yeah, so it's my hope to like truly understand everything. I'm not too worried about the illegal op codes, but yeah. As a full stack web developer for work doing a lot of React, I agree. LOL. Yeah, exactly. Breath of fresh air. That's what I need. So that's my hope. And I like it so far. Okay, so what I'm doing here, basically, I want to make this bigger, which we can do here. Cool. I'm guessing you're probably familiar with this website. It's pretty nice. So this loop takes, for the example of the number 4, this is just taking, or it's basically writing to memory, which I can put here actually. I don't want to change that just yet, because I think this is fine, but I'm not 100% sure. Well, I guess I would get a syntax error if this is not okay. I think this is fine though. Anyway, we're writing to memory. It's gonna write. I believe it's either 1 2 3 4 or 4 3 2 1, just in memory, basically, as a start. And then I want to output that, which I did before using the stack, but I wanted to switch from using the stack to just using memory. And yeah, I've learned a few things here because I didn't, yeah. I was trying to do everything just with the stack and the 3 registers, and I was running into trouble. So now I'm doing, yeah, I'm actually incrementing here. So I just learned that you can do this. So I'm treating this like a pointer. So I just want to take what's in memory here and output it. So we're loading in memory, then we're incrementing it like a pointer. And we're sending whatever's in X to A, then we're writing this out. So this will output, basically. And then we're incrementing Y, because that's the offset here. And then we want this loop to end. So that's where I want to do a compare. And want to do a compare. I've got this input value. Let's see here. I think, yeah, this doesn't work. CPY is just, I believe it's just comparing with the accumulator. Or sorry, that doesn't make sense. CPY is comparing with Y. What am I saying? But these, yeah, CPY is comparing, okay. Not really familiar with this site actually. It's nice though. 6502 stuff I did was in VS Code with some extensions. Oh, okay. Yeah, this website's nice. It's got a full tutorial. Yeah, they built it in JavaScript, and there's a bunch of nice features. There's a debugger. You can look at the memory as well. So, all right, let me just think. I need to compare this initial value, which I'm loading into A, but then I'm not really using it. Oh, right. So the reason I wanted to subtract, we're incrementing Y, and y starts at 0. Okay, let's just start with y at 1. How about that? Start with y at 1. And we have this offset. But then... we won't... No, we want it... I want it at 0. Wait. No, we can start with 1. Okay, I get it. And we'll do 1 less than this. 1 less than that, I believe, is 1 FF, right? So we increment y, and then we can compare y with input. The value at input, is that... I don't know if that works. I think that works, yeah. I think that works. And then branch if not equals... loop 2. Let's see. I mean, this has a chance of working, but I kind of think there's going to be something wrong. Wait, so it almost worked. This is basically outputting... Wait. It's outputting... I believe it's outputting 4, 5, 6. If we check the notes... 4, 5, 6. Yeah. That's not what I wanted. And so let's see what's going wrong here. So let's start at the beginning. So we're defining input as memory location 1, defining memory as memory location 2. This I'm treating as the input to the program for now, so inputting 4 as an example. Initializing y at 0, and we are storing this x value of 4 in input. So we're treating that as the input to the program. So then we enter our first loop. STX memory. I don't think this is a problem, but let's just switch this back. So starting in this memory location, we're storing x value, and there's this y offset. Decrementing x. So the first time x is equal to 4. Now it's equal to 3. Y is equal to 1. We're comparing the x value with 0, and then we're looping. So x will continue to get decremented. Y is incremented. So I believe this is writing into memory, starting at this location. It should be writing basically 4, 3, 2, 1. Is it writing 0 as well? No, because it writes first and then it decrements. Once x gets to 0, it exits the loop. So it should be writing 4, 3, 2, 1 into memory. So now we are setting y equal to 1. Oops. And now we are loading into x, whatever's at memory, which is this location. I see. So this increments... This doesn't do what I thought it did. I thought this was going to change this to the value 3. It doesn't do that. It does... It looks at this memory location and then increments the number at the memory location. That's why we're getting numbers that are bigger than 4. So that's different from what I thought. Oh no. Oh no. So I don't have something that's going to function like a pointer. What am I going to do? I want something that's working like a pointer, but... okay, loading memory into X register. That's good. I guess we'll go back to having this y offset. Kind of going around in circles here. But I can see already, like, you have a lot more limitations with assembly that I'm not used to as a programmer. I'm having to learn new techniques in order to handle these limitations. That's interesting. So LEY starting at 1. Are we really using the A register? Yeah. How are we going to increment through this memory? We need the Y offset thing. Does that work with LDX? Let's just check. We'll get a syntax error if that doesn't work. No, it works. So and we're getting, let's check the notes here. Cyan is 3. So as output, we're getting 3, 2, 1. Possibly 0 as well. But, right, because we don't need this line. So we're taking the X value, sending it to A. This is outputting. I just want to see what happens if I change this to 2. It should shift everything over by 1, I think. Wait a second, what? It didn't just shift. Oh, because we're using Y. We're also using Y for the, for that. Okay, forget that. So this here just outputs the information. I see, but LDX memory, we actually want memory minus 1. Getting a little complicated here, so we're gonna do this. Now it's outputting 4, 3, 2. So I'm going to start writing comments. Set Y value to 1. This loads memory location. Transfer X to A. Write A. So this is starting with Y as 1. So we're writing to the first write is to the first pixel, basically. Obviously this increments Y. I see. So we want to increment Y after the compare. Okay. That's actually working the way it's supposed to. So it's outputting 4, 3, 2, 1. Cool. I don't know why it starts adding these. Oh, wait, this is not my code here. Hold on. Where's my code at? Here. Okay. Yeah, so this is working the way it's supposed to. It outputs the values 4, 3, 2, 1 here. Hooray! Now I could stop here, but I want to keep going. I like this. I'm not stressed or anything so far. This is cool. So the medium-term goal here is to make a function that outputs permutations. So we've got 4, 3, 2, 1. So I'm remembering the algorithm I want to do. We actually want to start with 1, 2, 3, 4. But we have 1, 2, 3, 4 in memory. Is that correct? No, probably not. We have in memory, we have in memory 4, 3, 2, 1. So I could change this by, instead of decrementing through this, incrementing and then comparing against input. So up until 30 minutes ago, I only knew how to make a loop by starting with a high value, decrementing down until it was equal to 0. And that's how this loop works, this first loop. And so in the last 30 minutes, I've learned how to do it differently, where you're starting at 0 or 1 and then incrementing upwards and then doing the compare, which was not hard, but I'm learning. So that's good. So now I want to go back and change this so that we are starting at the bottom and incrementing upward, because I want the output to be 1, 2, 3, 4 rather than 4, 3, 2, 1. Okay. So we are starting at y is 0. Okay, cool. Let's walk through what this does a bit. Maybe I'll add comments as well. So LDX is set x value to 4. I'm using that as an example input for the program. And then we have LDY, so set y value to 0. STX input is going to store x at input, which is a location of memory here. Okay, then we enter the first loop. What I'm going to do here, so this is store x at this location. So I want to just change this to memory, so it's sort of not hard-coded. We have the macro, the define up here. And I believe, well, I'm going to leave this sort of hard-coded because it's actually 1 less than the memory value down here, but that's why it's number 1 here. But I just want to make sure that this still runs the same. Whoa, we got a random orange dot over there. What the heck is that? Why are we getting a random orange dot now? What the heck is that? Did I do something weird? What just happened? Now it's yellow? Wait, what? Hold on, wait, what? Okay, let me refresh the page here. I don't know what the frick is going on with that. Assemble, run. We're getting weird orange dots. I don't know what that's about, really. Maybe as we go through, we'll figure out why the heck that's happening. I don't think it's a bug in the software here. Anyway. Store X at input. Okay, so this will store X at this memory location thing. Let's do that. Assemble, run. Getting random output in this in this place. I don't know why. Something wrong with my comments? I think my comments are fine. So we take the X value, which starts with the input value, which is 4. We take that value, so it starts at 4, and there's an offset of Y, which Y is 0 in the beginning, so it's no, in the beginning it's no offset. So I'm not going to comment that because I don't want to. I'm lazy. This decrements X. We'll just add comments for the viewers. You know, they might want it. Decrement X. Increment Y. So, yeah, increment Y. So basically, we are writing to memory here. We decrement X. So what I want to be doing is, Y is not even used, Y is the offset, okay. I want to be incrementing. Right now the loop, the iterator of the loop is decrementing, and then we're comparing against the value of 0. So can we reverse that? I think we can. So we're going to compare X to input, which is going to be the number 4, and we're going to be incrementing X. Increment X. Okay. So X we want X to start at 0 actually. So after we've passed X over to this input value, and then I want to load into X the number 0, sort of initializing X as 0 here. So at first it's going to write the value of 0. Then things get incremented. We compare against the input, branch if not equals. So let's see what happens here. So now it's going 0, 1, 2, 3. I would like it to start at 1 here. And unfortunately we need to, but see what's going to happen here is that it does 1, 2, 3, and then, so what we're going to do is we're going to increment X after. We can increment both of these after the compare. Okay, and so now, what just happened? Oh, good Lord. What was that? Obviously our loop broke. Compare X against input. So X starts at the number 1. Writing that. Comparing against input. Oh, I think, wait, what? So these are changing the flags. Ouch. So I need to check about, somewhere in here is branches and control flow and that kind of stuff. And I believe, yeah, we talk about that here. Branching. Got to learn about that a bit. Okay, so branching logic. BNE is branch on not equal. Yes. This describes the program that they gave us an example. Usually use labels with branch instructions. When assembled, though, this label is converted to a single byte relative offset. Number of bytes to go backwards or forwards. So there's a maximum of 256 bytes there. Otherwise, you need to use jumping like JMP Learned that before. The opposite of this is this. BCC and BCS, branch on carry clear, branch on carry set. So I'm getting the sense that the increment things are messing with my flags. But maybe, am I allowed to increment one of them? I kind of doubt it, but like, we could actually just be incrementing y here, it doesn't matter. And then, no, it's still, that doesn't fix it. So this is messing with the flags that I need for this branch on all equals. But it was working down here as expected. That's why I don't understand. The heck? Why would that be? CPX input. Start. Now here's where maybe the debugger would be good. So let's see if we can switch on the debugger. Step. Oh, so we want to reset and then step. So X gets set to 4. Step. Y is set to 0. STX input. Now X is 1, so we're here. X is 1. So this program counter, let me just see how much that jumps by. It's at A, B, D, E, 8A. Okay. So it starts, okay, 0 like that. 2, 4. So it jumps 2 at a time, I guess. 6, 8. Okay, it jumps 2 at a time. All right. So let's go back to where X was set to 1, which is right here. So we're here. Now we're jumping into the loop. So this is like the number 10. And so presumably we wrote to memory here. We wrote the number 1, which is X. Now we've incremented Y. That's why Y changed here. CPX input. So compare. So this information probably has the flags. Okay, so I think this is the carry flag. We had a Z flag as well. Okay, so let's look up 6502 flags. We'll get the information on that stuff, huh? Oh, goodness. Yeah, so we have a carry flag. We have a 0 flag, so that's a Z flag. I believe that was handling... I forget, actually. We've got an interrupt disable, whatever that is, decimal flag, I don't know what that does. And then over here is an overflow. The V flag is an overflow flag. And the N flag is a negative flag. Okay. Okay, going back here. So, and then after V, these two flags are, it says no CPU effect. The first, this one is always 1 apparently. Who knows why? Maybe they were leaving an like extra space if they wanted to. They just had extra space and they didn't know what to do with it. Then the next one is called the B flag, and so the B flag. So it said no CPU effect. See the B flag. So what's that about? There are only 6 flags in the processor status register within the CPU. The value pushed to the stack contains additional state in bit 4 called the B flag that can be useful to software. The value of B depends on what caused the flags to be pushed. Note that this flag does not represent a register that can hold a value, but rather a transient signal in the CPU, controlling whether it was processing an interrupt when the flags were pushed. That sounds kind of advanced. I'm not going to worry about that right now. Okay. Whew. So we've got these flags. Coolness. Where are we here? I believe we just incremented y. So y is at 1. We might be on this part right here. CPX input. And so that should set the z flag, I believe. But I think we just incremented x. X is at 2 now. So this compare, the z flag is 0 because it's false, basically. And we just incremented x. Okay. Just incremented x, and now we should, let's see what happens. So it went from E here to 8, which I believe is the start. I believe it's here. I'm not sure if this is the next command or the current one or what, but anyway, so x is 2, and it should be writing that number. So increment y, it might be next. Let's see. Y is 1. So it probably just did this, and now y is 2. Okay. So now we just did this. Now we compare. Then we increment x. And then we loop again. So E goes to 8. But it hasn't. Actually, you know what? It's probably here. It hasn't done anything yet. Now it writes to memory. Now we increment y. There, it was incremented. Okay. CPX input should still be false here. It's going to loop back around. Now x is 4. We write that to memory. And now at some point the z flag should switch to 1. There it is. And the carry is 1. But now when we increment, let's see, I bet the z flag goes back to 0 here. Yep. So that's why it's looping forever. But the carry is set to 1. That's interesting. So hold on, let's reset and run. No, reset and then debugger step. So the interesting thing is that the carry only gets set here when we want it to break out of the loop. So I'm guessing I can do some kind of branching based on the carry. And I'm not really sure like why this makes sense, but I feel like it's going to make sense. So let's see here. Branching on carry or something like that. Branch on carry clear, branch on carry set, BCS. So BCS, can we do BCS? Wait, we want the opposite. We want, yeah, we want the opposite. BCC. Let's see if this is gonna work. So for some reason it worked. 1, 2, 3, 4 is the output, which is what I want. I have no idea what's happening with this this pixel over here. I'm just gonna ignore it. I don't want to. I don't know. There's something very wrong with that. But that's interesting. So let's reset. Let's go through this debugger a bit. I'm gonna be watching the program counter here for when we skip out of this loop. So, and you can look at the x and y values as well. And so x is 4, so we're gonna jump out of that loop at some point. Now we're at A, is that the new area? Let's see. LDY should be set at 1 soon. So x is 5. That's going to push us out of the loop, I think. Yeah. So now this just got executed. So we're probably here. And soon x will be loaded, or sorry, load into here. Yeah, load into x, whatever's at this memory location. So x should change soon. Yeah, x changed to 1 here. And it's going to get transferred to the A register. So A just got changed, and then it's going to write out. So I suspect the first pixel is going to appear here. Yep. Cool. This debugger is really nice. I really like it. Okay. So we just did this. Now we do this compare of the value at y, which is 1, with the value at input, which should be 4. And so z and carry are set to 0. Now we increment y, should change to 2. Now we branch on not equals to loop back. So wait. So I think what's happening is that this is also looping forever. That's why earlier it kept saying stopped, stopped, stopped. So I think this is looping forever, but the output was becoming 0. And so we just didn't notice that it was looping forever. So I think this is a problem, which we can fix the same way we fix this one. I think that's what's going on here. And so where are we? We just incremented y, I think, and I think we're going to branch back. Let's keep an eye on the program counter for the branching. Yeah, it went back. So I think we're either here or here. I'm not exactly sure how that works. We stepped in here. Let's watch for this one. Is it this one or the next one? It was here. So we just did this. Now, STA, CPY. That's interesting. This N flag got changed. I think next is increment Y. Yep. Go through a little bit more. I'm watching for the transfer of X to A here. Happened. Let's then we compare. We incremented Y. Watching for X going to A. There it went. Now the STA one. Now next we're doing the compare here. So it's going to compare Y, which is 4, with the input, which is 4. So it should set these flags. Yeah, set the flags. But now when we increment Y, this will go to 0, but the carry will still be at 1, I think. Yeah. And now, unfortunately, it's going to keep looping. Yep, it's looping forever. Dun dun dun. So what I want to do is this kind of thing. So, and I just want to check again. No, let's, that's why the pixel is getting, that's why we have this bug with the pixel. Aha, strange bug. So I just want to get into the second loop here. Boom, we're in the second loop now, and then I want to watch this carry flag. Yeah, okay. So we should be able to do this, but just in case something weird happens with low numbers, with low input values, I want to make sure that the carry starts at 0. So we're going to clear the carry. That's a CLC command. Clear the carry. And then I'm going to use this BCC thing to loop instead. So run, and we don't have this weird bug. The X and Y values aren't going crazy, and I think everything is good. So if I undo that, I think we're going to see crazy X, Y values. Let's see. Yeah, you saw the Y value went nuts. And actually, the whole thing is bugging. It won't let me assemble it again. I think. Maybe, oh, you know what? It's probably just that I have to change something, then it'll let me. Anyway, so it seems to fix the problem. If I have this like this, we'll watch the Y value, run, it went nuts. BCC, whatever that stands for. It stands for, of course it's not the British news company. Of course it's not that. It's branch on carry clear, meaning when the carry flag is 0, we branch. So the carry flag switches to 1 here when we want to stop with the branching. All right, so I believe that's running the way we want it. The output is 1, 2, 3, 4, which is what I want. Whew, geez. So, what do we do next here? Do we keep on going? I think we do. This is quite interesting already. I'm going to copy it to a new thing. What I am going to want, let's go up instead. Simpler, we'll overwrite some simpler program. What I want it to do now, I need some kind of function that transposes two items in memory. So let's do that. So this is the input or the output function. So I'm going to call this write out, and like that. I think that given enough time, it will sort this out. And so this is the last thing we do is we write out. I need to swap things in memory. It's a transposition. This is kind of the more technical name. But we'll write some it's going to work like a function. So we'll have this swap function. I got to use the restroom real quick. I'll be right back. Okay. So I can see why this is making me learn why this stack is important as a concept. I've learned about the stack before, so I know how it works, but it was all sort of just an abstract, like it was just information that seemed interesting. I've never actually really needed to care or know about it. And now I see, because if we're going to treat this as a function, we don't want some hard-coded place in memory as input. I mean, we could do it that way, but it makes more sense that somewhere, any random place in our program, basically if we want to use this function, and let's say we have two numbers as input, we just push those two numbers onto the stack. That's our input. We use the function. We do the function, and then we pop those two numbers because we don't need them anymore, and we return control flow back. And so what that's going to allow us to do is have basically nested functions. The way the stack, normally works. That's how it normally works. So I see that that's a really valuable sort of way of doing things. So we are going to have two inputs needed on stack. And so let's say, and then you have to think like, are we going to be clearing? What I don't understand is like, These functions might clear the registers and all that. That's where things are really... ouch, right? Is that just a painful reality of programming in assembly, I guess? Maybe. So as much as possible, we'd like to not mess with the registers, but I think it's gonna be inevitable that I think we do need to mess with them. So, also, can I put other things here than just Y, right? I imagine I could put A or X. Could I put another number that is stored in memory somewhere? This I'm not sure about. Relative addressing is used for branching instructions. These instructions take a single byte used as an offset. That makes sense. A single byte used as an offset. So I think I just understood something, why these have like an IP here. I think it's implicit. It's meant to be implicit addressing. And the reason they use IP instead of IM is that IM is taken up by this immediate, whatever that is meant to be about. So, yeah, these things, they don't deal with memory locations, so they're said to have implicit addressing. The argument is implied by the instruction. Implicit addressing. Okay. Then we have indirect addressing. Uses an absolute address to look up another address. So I think whatever value is in here is then used as an address. The first address gives the least significant byte. Yeah, I don't get it. So we'll look at, they say it can be hard to wrap your head around. Let's look at this example here. Hold on, my music stopped. How dare you stop my music, YouTube, like it always does. Very annoying. We'll get a little Oppenheimer music going. That's the best for doing this kind of stuff, huh? Feels very dramatic. So, alright, let's step through this and figure out what it does. Loading the number 1 into the A register. Store what's in A at mem location F0. I think this is going to end up being like a pointer. Okay, load the number into A. Not sure why. Store what's in A at mem location. It'll be one more than before. They should have some explanation because I actually don't get it. In this example, F0, I like that name, F0, contains the value 1. And F1 contains the value CC. I don't want to think about what that is, but it's a hexadecimal number. The instruction jump causes the processor to look up the 2 bytes at F0 and F1 and put them together to form the address CC01. So it kind of does it in backwards order, is that right? Because F1 contains CC. Yeah, it's sort of backwards order. And forms the address CC01. Okay. But why is it 0, 0? That I don't get. Like, I would expect it to be jump, and then it would be F1, F0, because it goes to CC01. That would make sense to me. That would make sense to me, but let's look at this. They say they explore more, or they explain more here. Jumping is like branching with 2 main differences. First, jumps are not conditionally executed. Second, they take a 2-byte absolute address. For small programs, this second detail isn't very important, as you'll mostly be using labels, and the assembler works out the correct memory location from the label. For larger programs, though, jumping is the only way to move from one section of the code to the other. Yeah, because they said, I think, well, never mind. Jump is an unconditional jump, JMP. La-dee-dee-la-dee-da. There is down here. So this will, the color associated with number 3, it goes black, white, cyan, red. No, sorry. It goes black, white, red, cyan, I think. Cyan, yeah. I don't know what's with these. Just giving it space. So then we've got jump to subroutine and return from subroutine are a dynamic duo that you'll usually see used together. JSR is used to jump from the current location to another part of the code. RTS returns to the previous position. It's like calling a function and returning. So I'm guessing maybe if you did a break, it would just stop and then go outside of the label, is my guess. And then RTS returns. But let's, I just want to Google like 6502 difference between break and BRK and RTS. Oops, BRK and RTS. Hello, Ahmed Naal. How are you doing? Can somebody please explain to me what happens to the stack when BRK is? I feel like it would do nothing to the stack. The stack should end up at... Oh, it does mess with the stack. Hmm? I'm confused. As others have said, the stack pointer decrements as it pushes. Senior thread on star dot. Maybe I can add a little more. What's up? How's it going? Where are you from, Ahmed? Blah, blah, blah. Sorry, this is really small. Has been pushed onto the stack too. Some complicated details, huh? I don't want to think about these complicated details yet. Really don't. Please. Please don't make me think about complicated details yet. I thought the PC, meaning the program counter, would be the address of the next instruction rather than the BRK itself. That's common with JSR, where the address on the stack is the third byte of... Oh, God. Good Lord, I don't want to think about it. This is too advanced. No, no, go away. Back to my happy place. Oh, Maldives. That's cool. Don't they speak French there? Tu parles français? Oh, you want to donate to me? That's very kind. You're the second person to ask for that. Want to donate. Let me get the link, I guess. Hold on 1 second. How can I get the link here? So I'll log into Streamlabs. This will take just a minute. 1 second. Maldives. Let's see. Log in with YouTube, I guess. Looks like we got a couple of subscribers today. That's nice. Thank you all for that. Okay, I'm just logging into Streamlabs. I think I can get a link. Yeah, we're logged in here, and let's see. Set up tipping. So I think let me see here. I got it in a second. Hold on. You might be able to do it. I'm gonna paste the link. You might be able to do it here, possibly. Let me know if that works. And the notification should come up, but I'm not 100% sure. It should work, though. I appreciate it. So jump to subroutine. So yeah, it's going to be like function and returning, like using a function. Processor knows where to return to because JSR pushes the address -1. So JSR pushes the address -1 of the next instruction onto the stack before jumping to the given location. RTS pops this location, adds 1 to it, and jumps to that location. All right. That sounded confusing, but I think we're going to understand this with an example. So this should go to init. We do this stuff, and we return. So it's probably, then it's going to go here. It's going to do loop, and then it's going to do, yeah. I get that. It's going to go to the init label, then it returns here. It's going to go to loop, the way you would expect. Do let me know if you try, because I want to thank you if you tip me. Somebody asked months ago, and unfortunately I just I didn't know anything about it. So but at least they got me thinking. And if you do tip, you'll be the first person on this channel to tip. A lot of people ask about the super chats. Unfortunately, I can't get this set up until I have at least 1,000 subscribers. But even $1 or 10 cents or even a penny is appreciated, frankly. Why not? Okay, so okay, so it sounds like it using JSR and RTS. I think I get it. So back to what I was trying to do. I actually even forget what I was even doing. Here I am. So I think we can kind of make, so we can do jump to subroutine, loop 1, and then here, that's interesting. Wouldn't it just return automatically? I don't know if it will. I guess not. I guess, unless I put RTS, I think it'll just continue down here. So RTS. And let's actually comment out this part, because we're going to check after if this is going to work. Then we do JSR loop 2, but now it's called write out. And then that's the end of the program. But we need this to work. We need this first. And then write out. So let's see if this is going to work. And yeah. So it's outputting 1, 2, 3, 4 essentially. So, yep. 1, 2, 3, 4 is the output. So that seems to be working. So this is like the, what do you call it? Well, it's like the main function, if you will. And this is basically initialization. Maybe I should put this in a thing. I'm treating this like the input to the program. So like if we change this to number 3, it's just going to output 3 pixels, which correspond to 1, 2, 3. The colors are down here in the notes. So 0 is black, 1 is white, and so on. And there's 16 different options. So yeah, but I'm going to keep it as 4 for now. The question is, do I want to have like an input or an init function? Let's do that. Let's have ourselves an init function. So init, I'll indent these, and then actually do we want to RTS, and I think we can come up with a better name than loop 1 as well, but JSR init, still working. So loop 1 is writing to memory. So write to memory. Let's change this with the underscore. I don't know why it starts underlining all these things. It's a little annoying. Now we have a problem I introduced. 37, line 37. BCC to memory. Maybe it doesn't like. Oh, I know what it is. Need the underscore here. Okay, seems to be working. We just kind of reorganize things. So we have init here, write to memory, do some stuff, then we write out. Okay. So I want to just open Sublime Text. I just want to sort of save these things in case for some reason I lose them in the browser or whatever. Yeah, did I already lose some of the previous stuff I did? No, this is what I had before. Let me just save that here. 1 second. I'll just save it to desktop, whatever. 6502. I'm not sure what the file extension name should be, but also, can we change the syntax highlighting here? I doubt it has 6502. Nope. Maybe I should use VS Code. Let me bring that up here. VS Code. Now I doubt. Select a language. Huh. 6502 came up as an option. Wow. Look at that. We got syntax highlighting and everything. It's fantastic. Okay, stupid name. Let's change it to 6502 or should probably name it permutations or something, but okay, so we're cool. We're writing assembly now. We've upgraded a bit. I've got better syntax highlighting. It's altogether going to be more. It's going to be more pleasant to write in VS Code here for sure, but I don't exactly have output yet. So for now, I'm just going to copy paste things back when I want to look at the output. Great. So we're trying to write a swap function. Oh, I've leveled up a lot in 2 days of this, huh? So we want to write this function that is going to swap 2 values in memory here. So first we need to push the 2 input values onto the stack. And then so I'm just going to use the X and Y registers freely. I don't know if that's going to be bad later, but let's see. So yeah, we want to swap these 2 values. Yep. But the input is supposed to be an address in memory. I wish those were. I wish I had something like pointers. Do we not have something like a pointer? Alright, maybe maybe I'll walk through. I've gone through most of this tutorial, I feel like. So the first one just sets some values. Basically outputs them, basically. So let's just get an overview and try to find any more relevant information that's going to help me. Since I haven't gone through this in any kind of logical order. There's registers and flags. Okay, processor status section. Processor status function. Did we talk about that? Did we actually talk about that? Anyway, we've got registers, cool. We've got a stack pointer. Program counter, yeah. So code starts at this memory address. Good to know. Last section shows processor flags. Each flag is 1 bit. So I've learned enough about it, about that stuff. So what does this program do? It adds a couple numbers. It adds some numbers, basically. Talks about the debugger, stepping through it. We've done that. It talks about overflow, carry flag. Important thing to notice here. So what is this code doing anyway? Storing this number in memory location 01, and then adding. This adds to A, so it's gonna add this number to itself with the carry. No, yeah, add with carry. To assemble, do this thing. Let's actually follow this because I'd like to learn about this monitor thing. It's saying to type it. Whatever. LDA 80. So that's the number 80. Load it into A. We store A at location 1. Add with carry. Whatever's at location 1. It'll add it to the A register. So that should be... It's 256, right? But it becomes 0? What's 8 times 16? It's 126, right? 80 plus 48, 126 times 2 is 256. And it should overflow and go back to 0. So it says check the monitor checkbox. And then step through these 3 instructions. So we're going to assemble. Hardodisku-san. Hello, welcome back. How you doing? Genki? We want the debugger on. Step. So reset. Step. So this is showing what's in memory. So this number should appear probably here. Here, okay. And then we're gonna add at some point. I never saw it add anything. Right, because it adds it to the A register, so it never appears in this memory here. Asa hayai? Asa osoi ka? Mada nete nai desu ka? 今日はアセンブラーやってます。6502 assembly。なんか昔の最初のファミコンとかのプログラミングはこの言語でした。ST1 as a value stored to the register should equal this, but because it's bigger than a byte. So the carry flag gets set, so we should have seen that. We saw that. Carry flag got set. As well as this, though, the 0 flag is set. The 0 flag is set by all instructions where the result is 0. Got a full list of instructions here and here. So this one looks like it's dead. I'll look at this another time. It gives you all the details of everything, which is nice. This is transfer A to X and blah blah. Okay, now we're in branching here. BNE, we've used this. I've talked about this yesterday, actually. First, we load the. Okay, this just explains what it does. So let's discuss this. This puts the number 8 into the X register. Then we enter this area of the code. This decrements X, so X will get decremented to the number 7. This writes it to the first pixel. That's a space in memory there. So the number 7 gets written here to the first pixel. Now CPX is a compare with X, so it's comparing with the number 3. That comes out false, basically, which means that... Let's actually step through this a little bit. Watch for when X gets set to 7. That's the decrement part, so that's here. And then this, we should have a color here on the first pixel next, so it's yellow. Now this thing, I'm interested in what happens with the flags here. So the carry gets set to 1, and yeah. The 0 flag is 0. So anyway, branch on not equals to decrement. So this is going to branch when basically when this was false. 3 is not equal to 7, so this was basically false, which is reflected in the 0 flag here. Think of 0 as false. So it's going to branch here, so it goes back, in other words. So if we step a bit further, we'll see x is going to get decremented to 6, and it loops around a few times until x gets to 3. And then x is 3, so we're here. And this color is going to change now, because that's what this line does. And then now we're going to compare, and I'm interested in these flags. So I think the z will get set to 1. There it is. Now on the branching, this one, it's not going to branch. And so we can see in the PC, the program counter is going to increment forward by 2. So it went from 8 to A, which is the hexadecimal for 10. And so now we are here, and it hasn't, I don't think it's, it has not done this instruction yet. And this is 201, which is going to be the next pixel. So it's going to write the same color to the next pixel. There it goes. And then it's done. It actually keeps on going. Anyway, so that's how that program works. That's a nice little loop. Values in the x, okay. If the two values are equal, the z flag is set to 1. Okay. So it's just explaining everything I just explained. In assembly, you usually use labels with branch instructions. When assembled, though, this label is converted to, we've seen this before. You can only use these labels like when they're not too far apart. If the lines are like more than 256 bytes away, it doesn't work. So you need to switch to using jump instructions, which we learn about later. So don't use those labeling techniques when things are too far away from each other. Then instead of branch not equals, we have branch on equals. Try right and okay, blah, blah, blah. We also have branch on carry clear and on carry set. And I've actually used that already. Okay. We've talked about that. Let me read this. Memory monitor to watch the memory change. Starting memory location. So where is that again? Okay, we have a start and a length here. When we monitor memory. Okay, that's gonna be useful. So absolute addressing is pretty straightforward. Just references of place in memory. Very straightforward. We have the 0 page, so we don't have to write out the full thing here, but this is just the first 256 bytes of memory. That's called the 0 page. All right. Then we have this, which I believe is just an offset. Yeah, the value of the X register is added here. Oh, so you can actually put a... yeah, I need that. But I've always been doing it with Y for some reason. I wonder if you could do it with A. So we have 0 page X, we have 0 page Y. And so I guess we don't have it with A register, I'm guessing. If the result of the addition is larger than a single byte, it will wrap. Okay. This can only be used with these. Okay, so LDX, so for example, LDA, excuse me, for example, STA can be used with X, but STA could not be used with a Y increment. So it has less functionality here. So I should default to using X as an offset, because you have more options. Absolute X, absolute Y, absolute, it's basically absolute addressing with the X offset, absolute with the Y offset. So it's saying this and this. These are absolute addressing versions of this. Yeah, so it's with the offset. So the absolute Y one, again, can only be used with... oh, that's confusing because it's two different things. It's like maximally confusing. Okay. Immediate addressing doesn't strictly deal with memory addresses. This is the mode where actual values are used. Okay. That's like a pointer then. So is it? Oh, no. This is very different to the... No, it's just the number. Yeah, immediate addressing. It's not a pointer. And then we have relative. Relative is used for branching instructions. These it takes a single byte, which is used as an offset. So we're loading 1 into the register A. We compare CMP. CMP, yeah, it compares the accumulator with the number 2. So branch on not equal. So it is going to branch here because 1 is not equal to 2. And that's it. So this is never going to happen. Assemble them, do hex dump. Okay. Processor opcodes. Don't need to think too much about that. One and 2 are the arguments, and so these are just... I think it's just a direct translation. Basically, this is like machine code, essentially. That you're... Typically in assembly, things are just translated into machine code directly. So wherever there's LDA, it gets translated to this. Wherever there's CMP, it gets translated to this. D0 is the opcode for BNE, and its argument is 2. This means skip over the next 2 bytes. I see. It's just going to skip over these, and so that's why it skips these 2 and goes here, I guess. Or no. It skips, this doesn't have any, doesn't show up in the hex code, so it's this byte and this byte that's being skipped. So it skips over this, and then break is just the opcode 00. I'm pretty sure here. So blah blah blah. Try editing the code so that this takes a 2-byte absolute address rather than a single byte 0-page address. In other words, change that to that. Okay. Assemble hex dump. So now we have 2222, and also, so I know this is really small. 22, 22, but also this changed from 2 to 3 because it has to skip over more space to get to there. Reassemble the code and look at the hex dump again. It changed to 3. Yep. Implicit. We talked about this. Indirect. Indirect addressing uses an absolute address to look up another address. The first address gives the... Oh, yeah. So this was complicated and I didn't really understand it. We talked about this. I still don't really get it. Put them together to form this address. Semblance... okay. But can we use that as a pointer? I think, yeah, I think I can use that as a pointer. I'm gonna use the restroom and think about this. So I think I'm gonna play around with this till I understand it, because I think I can use this as a pointer. Let's see. So it puts 1 in there, and then it puts CC in there. Yeah, this is looking like it works like a pointer. But I just don't understand. I don't understand why it's not F1, F0. That I don't understand. Let's look at the hex dump. So we have, this is the first instruction. This is the second instruction. We have LDA CC. So CC gets put into the A register. I'm gonna assume this is, yeah, this is STA. It was here as well. So F1, so it's not the number F1, it is the memory. The memory location F1, okay. And then we have a jump. it receives, it's just the order is reversed. That's just confusing me. The order is reversed from what I would expect, so... I don't get it. Anyway, this is absolute. So it doesn't seem... I feel like absolute... I mean, it's absolute, I mean... Like, I feel like I'm always going to be using labels to jump around, but sometimes I feel like I need pointers. Frustrated. I'm frustrated. Then we talk about the stack. Looked at jump. GSR RTS, we did this. So it's talking about macros. These define things. Okay, so this is good. Why does it do that when I highlight it? Anyway. So this is the number 12. It gets put in there, and then if you want to use it as the number 12, you need to put this pound sign. Okay. It's very cold, so I'm just warming my face. So this is all about their little game that they write where they make snake. And that's the whole thing. That's the whole tutorial. And there's some things I still don't understand. So I'm going to look for more tutorials. 6502 tutorial. That was a great tutorial though, but you often need to look at more than one. Just got a list of them. Let's just look at this one now. Talks about, like, yeah, lots of basics of computers, like binary, hexadecimal, la-di-di, la-di-da. Why learn this? Why 6502? I'll make this bigger. This really holds people's hand pretty heavily, which is not bad, but Deeper dive is available here. Carry, addition. Yeah, we added the number 2 to the number 1. And this is probably just outputting or something. There's a decimal flag. Yeah, dividing by 2 can be done with binary shift. What's it called? Bit shift. So we have this ROL is an LSR anyway. Goes to the right, and this one goes to the left. So if we go to the right, should be dividing by 2, I think. We can use this to divide by 2, yeah. These and the other one is going to multiply by 2, although there's going to be overflow. Okay, next one. Multiplication. I don't know why they're jumping into multiplication. We have to implement that ourselves, right? Or maybe not. I don't know. It's getting a little complicated. Yeah, they're doing their own thing. So I feel like this was a bad jump, because they start really slow holding our hand, and now they're jumping into this, which is very bad pacing, in my opinion. Just my opinion. Let's see what else we got here. We got the NES stuff as well. Oh my god, I should make my own tutorial eventually. I mean, look at how bad these are. Whoever decided to use this. Terrible on the eyes. Okay, I remember this actually. I've seen this before. So they've got a tutorial for NES programming, which actually I'm definitely interested in doing. Not just 6502, but NES stuff specifically as well. Should I make it bigger? Like this. Okay, like this, I guess. So they're gonna teach us stuff. Cool. Yep, they're gonna teach us the stuff. It's great. Oh, so there's another tutorial thingy. All right. I guess we're supposed to start with that. Hooray. I might like read more detail because I am interested in history and stuff, but not for the stream right now. Might read more detail some other time. So they're talking about what an opcode is, and they're talking about the LDA instruction and the SDA instruction. Yep. And they talk about the website we've been using, actually. So let's take a look at this code that they wrote. So this is passing 0 into the A, register. Then it writes it to memory location 0, 0. And then we're going to take the number 5 and write it to memory location 0, 1. Then we put the number 0 into the Y register, put the number, or excuse me, we put not the number 0, but whatever's at the Okay, yeah, they just don't have the $sign because it doesn't really matter. $signs for hexadecimal, right? Pretty sure of that. I just want to verify. I don't know why. Oh, you can use binary numbers like this. Okay, so it's still the number 0. It's just written in decimal instead of hexadecimal, but it doesn't matter. So now they have this parentheses thing. So indirectly store the number 1 into the memory location. Is it using whatever's at in memory location 0? This is storing 0 into Y. This is storing load the value of 1 into A. Oh, because Y is 0. Sorry, this is not loading into A. This is store A. So store A, which is the number 1, into this memory location, which is, they're saying this. We created it earlier on the top. Okay, so here's where the parentheses works. So this is what I can do as a pointer. This is what I want. It's whatever is at memory location 0. And memory location 0, let's see here. I thought it has 0. Getting confused. Are these reversed again? But why is the number 0? Do they explain about the parentheses? So let's see their explanation. I don't get it. I feel like it's been explained to me so many times and I just don't get it. We actually just converted a 16-bit number into a real memory address by combining two 8-bit numbers. I'm here, lower and upper. And put a value there so a pixel appears on the screen. With this, you have to wrap the address with parentheses if you're using indirect addressing. If it's X, you would wrap the whole thing. Like this. What? I appreciate their explaining, but I think it is very poorly explained in my opinion, my personal opinion. But we'll try to understand it anyway. Yeah, I just don't get it. I think it's poorly explained. I don't get it. I don't get it. Cool. So, again, I'm critiquing a tutorial here. They're just introducing assembly right here. And for some reason, before even introducing this stuff, or explaining this stuff, they're talking about this complicated indirect addressing method that differs between X and Y here. Is this just a syntax difference? I don't. I feel like this is extremely poorly explained. I'm sorry. Let's see if we'll make sense of it as we go through here. So this is for addition. So this is going to be the number 255 into A, and then we're adding 2. So we should get the number 1 back. Accumulator would be 1 with the carry flag is set. If the carry flag is set. So it wrapped. There was overflow. Subtracts instead of adds. But it also subtracts the carry, which is weird. That must be useful for something. No problem. No problem. Subroutines. So let's look at their code. 0 into the Y register. My brain is... Whew. It's been a lot for today. I want to keep going. I want to... Ideally, I would like to understand this indirect referencing thing. I want something that acts like a pointer. And I feel like they explained it extremely... I'm sorry. I think this is a very poor explanation. I have to say, I apologize, but I think so. And I just really want to understand that, if possible, today. This is fucking hard. I'm sorry. This is so hard. All right. Brain is turning into mush, but this is the actual number 0. We're going to... I wish I could comment this. So let's take this into VS Code and just add some comments. Yeah. So I'm going to write my own comments here. So that is a decimal number. But it's send 0 to Y. It's amazing we can use tab. Send 0 to A. Send A to memory location 0. So it's going to send the number 0 to memory location 0. Hooray. Send the number 5 the number 5 to A. Send A to memory location 1. So it's going to have... So in the first iteration of the loop, in memory, we basically have 0, 0, 0, 5 in bytes after the first iteration. Send the number 1 to A. Send. So this is the instruction I don't understand. So hopefully we'll figure out how this works. Increment Y. So I don't know why they have all this space in the middle, because it's just going, it's just a big loop. Yeah, I don't know why they have a space here. So we'll run it. So it never exits the loop. And let's think about this. So we had memory, in memory, we had 0, 0 and 0, 5 actually. Yep. Oh, and I didn't actually understand how this works. That's a bummer, but I think I have to... Let me think. Yeah, I gotta stop. This is... My brain is mush. When I sit down to do it next, I will try to understand this shenanigans. I believe this acts like a pointer, and I think I can figure it out, but I have to... I need to have a fresh mind. I need to sleep at some point, and... that will be the next phase. So we actually, I mean, this is huge progress for day 2. Wrote all this stuff. I'll put it in the description of the video after I'm done here. Hooray. Thank you, everybody. And let's see here. I don't... Somebody was talking about donating, but I don't see that it worked. Unfortunate, but okay. Thank you everyone, and have a good rest of the day. Thanks for the likes and subs. Thank you.